Hello everybody, and welcome to the problem review session for the 2021 Fall Math Meet organized by NanoMath. Actually, this is also Ask Math Anything, although it seems like for the last two sessions, last one and this one, we've been using this particular session to go and talk about some wonderful problems that some high school students chose to write. So last time we did something that was made by Phillips Andover Academy students, and this time it's by a group called NanoMath. All right. Let's go and see what their questions were today. I haven't looked at them yet, so I think I'm going to have to struggle a bit on these. Let's see what happens. Okay. How many regions does the graph of xy times x plus y times y plus x times x plus 2y times y plus 2x equals to 0 cut the xy plane into? What is this about anyway? This is a graph, you're saying? Well, I see some y's, I see some x's. I'm used to thinking of graphs as y equals something x. Well, let's see. What could we do here? I see that there's a whole bunch of things multiplying to be 0. So actually, if I'm looking for what values of x and y make this whole thing into 0, it'll be anything that makes any of the terms equal to 0. So I guess I could think of it like this. So this equation is the same as the equation x equals to 0, or y equals to 0, or x plus y equals to 0, or y plus x equals, oh, that's the same. I'll just use the same color, y plus x equals to 0, or x plus 2y equals to 0, or, I'll put the or over here because I don't want to run out of space on the bottom, or y plus 2x equals to 0. Okay, well, I see that I have a bunch of different lines. I also see that if I want to use color coding, I should probably use this one in white. I'll write or y plus 2x equals to 0. Okay, now let's try to graph these. Oh, I see x equals to 0. That's like this. That's the y-axis. Y equals to 0. That's the x-axis. Now, this is the graph of any of the points on any of these lines works. Okay? So, for example, any one of these points in this y equals to 0 is on this particular graph. So, when I have that, I just mean I'm taking the union. I'm taking all of these lines that I draw. I also have x plus y equals 0, y plus x equals 0. Those are the same. Those look like this, a slope of -1. That's y equals -x. I also have x plus 2y equals to 0. What is that? Well, that's, if I think about it, that's y equals -half of x. So it's a slope of -half. Maybe it's like this. Okay, let's pretend that that's the graph of x plus 2y equals to 0. And in this guy, this is y equals -2x. So that's just a slope like this. Oh, this is such a pretty picture. All right, so in that case, how many regions do I have? Well, 1, 2, 3, 4, 5 times 2 makes 10. Looks like the answer is 10. Let's see. So I think I see 10 pieces. I guess one of the tricks on this question was that the x plus y and the y plus x are the same thing. Let's see what happens. 10. It's good. All right, let's go to the next question. But before we go to the next question, what I'm seeing is that my shirt looks a little bit too bright. So I'm going to turn the light down very slightly, or turn the brightness down very slightly. I'll be right back. I don't know if you can tell there's any difference at all. I barely can tell there's any difference. I think the problem is called I'm just wearing a shirt that's too bright. Okay, let's keep going. Let's keep going. Next question. Why am I moving that mouse? No, the slides are here. Let's see. Define f of n to be the total area enclosed by... Ooh, this is when you round something up. So the round up of x times the round up of y equals to n. Let n be the number that maximizes f of n on the interval as n goes from 1 to 900. Calculate n plus f of n. What is this about? Total area enclosed by... But that's funny. I'm having trouble with this because I'm trying to think about whether or not it's even defined. So, for example, if I had n equals, like, I don't know, 17, okay? If I have n equals 17, which is a prime number, then the only way I could get two integers multiplying together to be 17. It's like 1 times 17 or 17 times 1. Oh, I think that's okay. That's okay. That's okay. Okay. So let's think about this. I'm trying to understand what in the world this even means. Okay. So when I look at questions like this, I'm like, let's try it for some smaller values of n. 17 is too big. Let's try this for n equals 3. I just want to know what it even looks like. If I have it for n equals 3, now the only way to multiply together to make 3, two integers multiplying together to make 3, are 1 times 3, 3 times 1, and that's it, right? Well, we've got to be careful. There's also negative 1 times negative 3. And there's also negative 3 times negative 1. Aha! And now if I'm thinking of how in the world I could get the round up of x, also called the ceiling of x, to be 1, and the ceiling of y to be 3, let's draw some of these. So here's my coordinates, okay? What part is in here, which is where the ceiling of x, rounding x up is 1 and rounding y up is 3. Well, if I round x up to 1, then that's like x is between 0 and 1. And if y rounds up to 3, y is between 2 and 3. So actually, that first thing is giving me this. So this first thing just gives me a 1 by 1 square. That's kind of cute. Now, technically speaking, it should not include the bottom edge of this, because if I have y equals 2, when I round up, it's still 2. But if y equals 2.1, well, then it rounds up to 3. So what I'm seeing here, by the way, is if I draw all of these, it looks like I'm just going to get a bunch of these unit squares. This is the second one. Be careful with the negatives. If I round up to make minus 1 for my x, then actually my x is between minus 2 and minus 1. You round up to the next integer. Integer meaning round up closer to 0. And that's at the rounding up the x to be minus 1, rounding up the y to be minus 3, means that the y is between minus 3 and minus 4. Okay, so I also have one down here. I'm just drawing this so that we know what it looks like. And there's also one where the x rounds up to minus 3. Oh gosh, it's flying all the way over here now. Let's see. Minus 3, minus 4 is here. And the y rounds up to minus 1. So it's going to be something like this. So this last one that I drew here, the x rounds up to minus 3 and the y rounds up to minus 1. Okay, so if I look at this, I'm like, look at that. I've got 4 of these, and I have 4 of these. So it looks to me like f of n is just trying to figure out how many factors there are. Is that right? I think so, because x can be any factor. Actually, it's times 2, because I'm also allowed to use negatives. So f of n is just the number of factors of n. Times 2, times 2. That's what we see here. Because we're basically saying, how many choices do I have for this x rounded up? So that's interesting. I'm just commenting f of n is equal to 2 times the number of factors of n. Okay. So now what I need to do is I need to go and take 2 times the number of factors of n plus the n. No. Good. I was going to say, if you're asking me how to maximize this sum, that takes some effort. But you're telling me, no. N is the number that maximizes the f of n. So now I want to know, out of all the numbers from 1 to 900, which have the most factors? Well, how do you do that? If you want to have a lot of factors, I mean, if you chose the number 900, it's probably not 900, but let's play around with this, okay? So now let's see how many factors there are of a number. The number, no, don't write f. the number of factors of 900. Well, what is 900? 900 is equal to 9 times 100. 900 is equal to 9 times 100. 10 squared. And 9 is 3 squared. 10 is 2 times 5. So I have something like this. It could be 3 squared times 2 squared times 5 squared. If I did that I can find out how many factors there are now. This is a standard formula. I don't have time to teach it here inside this particular live stream, but you take each of those exponents and you add 1, each of those powers and add 1. So the number of factors of 900 is equal to 3 times 3 times 3, which is 27. But now the question is, can we do better? Is there anything with more than 27 factors? Well, now we can start to play around. You see, I wonder what would happen if I tried swapping a 5 to a 7. Oh, that wouldn't be good because I'd go over 900. But I'm basically saying, is it economical to be using a 5? You see, because the thing is that if this is a 5, I get 5 squared, and the 2 gives me 2 plus 1. But if I look at this, I'm like, if I had something to the first power, that's pretty cool because I'll suddenly get to have like that thing to the first power. That gives me the 1 plus 1, and I'll have maybe something else to the first power, another 1 plus 1. So, for example, what I'm saying is that 2 plus 1, which is 3, is less than a 1 plus 1 plus a 1 plus 1. But the question is, can I actually make those happen? Right now, everything is appearing twice. I'll just do another test. Let's see. I wonder what else I can do. This is where I'm just playing around. I'm like, what else can I do? What if I did the number like 2 times 3 times 5? What's that so far? That's 6 times 5. That's 30. Times 7. 30 times 7. 30 times 7 is 210. Oh no, there's no more space for anything else. So this is already 210. And if I wanted to go and, get this thing as big as I could, I'm just playing around to see if you can beat this number of factors anyway. I can go all the way up to 900. So let's just multiply this by another 4. If I multiply this by another 4, then that goes to 840, which is less than 900. Now let's play around with this, and let's just go and see what happens. So that factorizes as 2 cubed times 3 to the first times 5 to the first times 7 to the first. Okay? And that means that the number of factors is equal to, now you take each exponent, add 1, so it's 4 times 2 times 2 times 2, which is what? What is this number? So that's 4 times 8. Ooh, 32. That's more. And of course we knew that it shouldn't be, it shouldn't be that 900 has the most factors, or else it's just too easy. So that's interesting. I've just found out that I can get a number less than 900 that has more factors than 900 did. Then I have to stare at this and say, how did we get any advantage? Why was this a good thing to do? Well, this was a good thing to do because somehow, I was able to get another term, right? In some sense, each of these, the way I'm thinking of it is that each of these exponents lets me take an exponent plus 1. And there's a big gain when I suddenly get to have another thing and it's like a 1 plus 1, like 2. I get to double, okay? I've already seen from doing this that I can't get 5 things. There's no way to get 5 prime numbers multiplied together, because that would be requiring me to times 11 or more, and it won't work. It won't fit into 900. So I either have if I have 4 prime numbers multiplied together, these are the 4 prime numbers, 2, 3, 5, and 7. Is there anything I could do to do better than this? Well, if I try to give more of these powers to the 3 instead, that's kind of pointless, because if I put it into the 3, that makes 630, but I just get a 2 there. So it would be like a sequence 1, 2, 1, 1, which is less exciting than 3, 1, 1, 1. So if I use 4 different primes, actually the best I can do is this 32 factors. Then I'm starting to think, what if I have 3 different primes? Are there other things I can do with these 3 primes? Because, for example, I can shove more things onto the 2. Like, everywhere that I see a 5, I wonder if I should be just throwing more things into the 2. Like, right here, this is 5 squared is 25. I could throw 4 more 2's into there if I felt like it. Because 2 to the 4th is 16. Would it be better to throw 4 2's in there? Let's find out. So another option I could do is 3 squared times 2 to the 6th. Okay? I could do that because that's like throwing some things from the 5 into the 2. And I had 25, so I can throw 16 in. If I did this, this has how many factors? Well, it's 3 times 7, which is a puny 21. That's not very good. So this is showing that, in some sense, when I have fewer prime factors to play with, well, then maybe it's not so good. But I should be more careful. Actually, if I only have 2 prime factors, is the ideal way to be putting more of them on the 2's? This is a tricky thing where sometimes you need to do some testing just to go and compare. Like, usually when I'm distributing things, I want them to be more equal. I want to multiply things that are equal to each other. So, for example, what if I put 3 cubed times something? You know, like, put some more 3's and then, you know, have some less 2's. What if I did 3 cubed? What if I did 3 cubed? Well, the way I can think of that is if I'm trying to eliminate my 5's, because I'm only down to 2 prime factors, if I eliminate the 5's, I have 25 to play with. If I have 25 to play with, I can make a 24. That's close. 24 is 3 times 8. That means you put 1 more 3 and you put 3 more 2's times 2 to the 5th. How many factors does this have? This has 4 times 6, which is a puny 24 factors. Okay, so this is showing me that somehow it's a disadvantage to eliminate the 5 and put things onto the remaining 2 prime factors. And I mean, if I just think of it, can I just use just a single power of 2? No, not really. If I want to beat this, I would need 2 to the power 31, which is kind of big, a lot bigger than 900. So what this is showing me is that the best thing to do is to have more of these. There's one more thing I'd want to check, which is, what if I just leave one of the 5's? If I try to pull 2 of these into there, let's just do this last comparison. I say pull 2 because if I keep 1 5, I can get a 4. I can turn the other 5 into a 4, and that bumps this power up by 2. How many factors with 3 squared times 2 to the 4th times 5 to the 1st? How many factors? Well, that's 3 times 5 times 2. Okay, so that's 30, which is more than the 27, but doesn't beat this 32. So in that case, it looks to me like the best thing that I can do is indeed to have 4 of these factors, and 4 of these different prime factors, and then I'll get 4 times 2 times 2 times 2, 32, okay? So I'm going to say that my n is my 840. My f of n is equal to 32, and the question asks for the sum. So 840 plus 32, I think that the answer is 872. Is this right? Let's find out. No, it's not. It's 904. Ouch! It was wrong. Okay, well, whenever we do a question like this and we find out that it's wrong, then we need to go and see if we can learn from our mistake. 904. That's interesting. Well, that's indicating that the number is pretty close to 900 because I'm going to add some number of factors. Oopsies. So I need to add some number of factors, and you know, the number of factors is not going to be that big. What else could be around here? Let's see. So we're going to get numbers that are close to 900. How's 810? Is that what we should be doing? I'm just thinking to myself, what else is high? No, but it can't be 810 because if it's 810, I need a huge number of factors. I answered the wrong thing, someone said. What did I answer? Calculate n. Oh, f of n is 2 times the number of factors. It's not 32. It's 64. And we knew that. It's because it's not the number of factors. It's 2 times the number of factors. Oops. No. Not 32. Oh, I know what to do. It's 32 times 2. And that is equal to 64. Okay, Now we can add these. And now it makes 904. Now we're good, right? Because 840 plus 64, that's not a 9. It's 904. And what this shows is that you should always go and check your logic again. Because maybe after doing this ton of hard work, you sort of read the thing wrong or forget the last step. And it's like, oops. Okay. Well, thank you to everyone for making comments inside the chat as well. Let's see. What's the next question? Team round, number 10. Where's my team? Oh, all of you. Let ABC be a triangle with AB is 13, BC is 14, AC is 15. This is a very common triangle, the 13, 14, 15 triangle. We saw it last week as well on this MOAA, Math Open Andover competition. Suppose M, N, and P are points inside the triangle ABC, such that M is some midpoint. Okay, we got some midpoints. Let's draw this thing first. So I have some triangle, ABC, and it's not like equilateral, but the sides are kind of close to each other. The longest is AC, the shortest is AB. So I'll do it this way, AC and B. Okay, M, N, and P are points inside the triangle. Okay, so AB is 13 and M is the midpoint. Wait. What just happened? M is the midpoint of AP. What? Oh, these are strange. Okay, I've got some points. One of them is the midpoint. M is the midpoint of AP. P is the midpoint of CN. I'm wondering if it's some kind of like a twisty thing that looks like this. I'm just going to draw something, and I'm just curious if it looks something like this. So let's see. So M, I'm just wondering if this would work. M is the midpoint of AP. N is the midpoint of BM. And P is the midpoint of CN. Hey, actually it looks right. Okay, so it's this is what it is. And we need to find the area of triangle MNP. Nice. Okay. So if I have a question like this, actually you can usually use ratios to try to solve these kinds of problems. Is that right? Ooh, I'm seeing something. This is cool. Okay, here's what we're going to do. Let's suppose that the area that I don't know is called A. I don't know what it is. I don't know what is A. Now, can I label any other areas? I can. You see, let's look at this other triangle over here, AMB. And let's compare that to this triangle over here, which is this MPN. They have the same base, but how do their heights compare? Well, that's the midpoint, right? So that means the height of the bigger one is twice the height of the smaller one. That means that this is 2A. Somebody says that looks like a portal, I think. Okay, so what else do I have here? So that's 2A, and the same thing happens here, because you could think of this as the base of the triangle, and this as the base of a triangle. And now the base of the triangle, which triangle? Well, this is the base of this triangle, whose height is twice of this triangle's height. That means that, again, this is 2A. And the same thing will happen here. This is 2A. Aha. So what this means is that the area of this triangle in question is some fraction of the whole area. What's the fraction? Well, let's see. I've got 2, 2, 2, and a 1, which is 7. So it's 1/7, 1/7. So the answer is 1/7. 1/7 times the area of triangle MNP. Okay, now we just have to find the area of triangle MNP. Well, AB was 13, BC was 14, and AC was 15. I've seen this triangle many times before, so I actually know how you make it. But I'll say, if you didn't know how you made it, there's a formula for you that will save your life in these kinds of things, and it's a hero, or Heron's formula, or hero's formula, depending on how you write it. It's just that I have the 3 sides of the triangle, so let's just go and use this, this formula. Okay? So what's the area? It uses something called the semi-perimeter. Okay, so what's the area? Area is the square root of semi-perimeter times semi-perimeter minus A times, oh no, why did I call it A? I mean, A A now is like the length of one of the sides, okay? Not this actual A. That is so confusing. Let's just actually write down the side names. Let's call it AB. Semi-perimeter minus BC length. Semi-perimeter minus CA length. Okay, so what's the semi-perimeter? Let's find out. So the semi-perimeter is equal to, add up the 3 and divide by 2. If I add up 3 consecutive numbers, the sum is always 3 times the average, which is 3 times the middle. So that's 3 times 14. Semi means divide by 2. Oh, that cancels. 14 divided by 2 is 7. So that's just equal to 21. So now I can continue this. This is the square root of 21 times, what's left? Minus AB. So that's 21 minus 13. That's 8. 21 minus BC. 21 minus 14 is 7. And then 21 minus 15 is 6. Okay, so let's just try to make this actually work. The 21 is 7 times 7. That's nice because I see a 7. No, it's not. 21 is 7 times 3, which is nice because I see a 7 and I also see a multiple of 3. Okay, so let's see. So this is equal to square root of 7 times 3 times, let's make the 8 into a 4 times 2, and I have a 7 and a 6. Which is great, because now if I go and take a square root, I see 2 7s, so there's 1 7 left. Okay, and I have a 3 and a 6. Oh, I can take the 3 and the 2 and make a 6 out of that. So this 6 cancels with that 6, meaning that they combine, and when you take a square root, you just get 1 6. And then there's this 4, which is left over. Square root of 4 is 2. Terrific. So that's the area. So then the answer is 1/7 times the area, which is 7 times 6 times 2. 6 times 2 is 12. Let's see if this is correct. It is. Okay. Let's try another question. Let R denote the real root of the polynomial x cubed. Cubed? Wow. I don't know the cubic formula. Anyway, x cubed plus 21x plus 1. The infinite sum, which is absolute value of r minus r to the 4th plus r to the 7th minus r to the 10th, and so on, can be expressed as m over n, where m and n are relatively prime positive integers. Find m plus n. Yikes. Okay. Well, first of all, I'm like, what kind of a funny infinite sum is this? It looks like a geometric series. Can I do anything to simplify that first? I have r minus r to the 4th plus r to the 7th, and so on. Now, you have to be careful. If r was something whose absolute value is more than 1, this is going to, what we call, blow up. Meaning that we're going to get bigger and bigger and bigger numbers, and it will just not even converge to anything, because we'll be adding a giant number and subtracting an even more giant number and adding a ginormously more ginormous number, and it's terrible. So hopefully this r is absolute value less than 1. Okay? Now, if it is absolute value less than 1, then it's going to have a geometric series sum. This is a sum of an infinite geometric series, r over, that's the first term, over 1 minus the common ratio. And the common ratio is negative r cubed, so 1 minus it is 1 plus r cubed. So that's going to be the inside of the absolute value. That's just like, note to self, if there's a negative number, I have to turn it into positive at the end. Now, I'm curious, what is r over 1 plus r cubed if I know this? Well, okay, let's write that down, but just as r's now, because r is a root of it. So r has to satisfy that equation. R cubed plus 21r plus 1 is equal to 0. Okay, if I want r divided by 1 plus r cubed, I see something. I see what 1 plus r cubed is. R cubed plus 1 is just negative 21r. So let's just divide. It's r divided by negative 21r. So now I have, let's continue. So this is equal to r over negative 21r. So that's just going to add up to 1 over 21. No, it doesn't. It's because I did the absolute value already. I knew I want positive things, but if I want to write true mathematics, I better write negative 1 over 21. But this time I'm going to be careful. It says make sure that you take the absolute value. So the answer is 1 over 21. No, you have to figure out that you need to have relatively prime positive integers. So the m and the n are 1 and 21. That means that the answer should be 21 plus 1. So the m is 1, the n is 21, and the sum is 22. Let's see if this worked. It's good. Okay. Let's see. What else do we have here? Next question. So many words. Need a drink. Two circles of radii 1 are separated by a distance of 1 such that they pass through each other's centers. Already I'm having trouble understanding what this means, because how can you be separated by a distance of 1 and still pass through each other's centers? I bet it means that the centers of the circles are separated by a distance of 1. Okay, and then they'll pass through each other's centers because their radii are 1. Okay, let me draw that first, just to even know what we're looking at. There's 1. Hopefully that looks somewhat reasonable. These are two circles. And they pass through each other's centers, pretend. An arc length is chosen uniformly at random between 0 and 2 pi. And then a random arc with that length is chosen on the circumference of one of the circles. What is the probability that this arc contains both intersections? Okay, I see two intersections here. All right. So when I'm looking at this, it's like you choose the arc length randomly on one of the circles. But by symmetry, I can just assume you pick it on the left circle. Because at the beginning, we can be like, let's flip a coin. Either pick it on the left circle or the right circle. No matter which way your coin goes, the problem is the same because I could just like take a mirror and reflect it. Okay? So what I'll say is that let's just assume that we're picking a uniform arc length over here. Interesting. So actually, first you choose the length, and then after you choose the length, then you decide where it sits. This is a geometric probability problem. Okay? So what I'm going to do is I'm going to draw a chart. And the chart is going to say, based on that arc length that I choose, what's the probability that the arc contains both intersections? But given that I've already picked a particular arc length. So this is the arc length. And the other side is the probability contain both intersections. The reason that's important to have two different things is because, by the way, if your arc length is too short, like 0.1, if it's 0.1, no dice. It's not going to work. There's no way you're going to be able to cover both intersections. In fact, the minimum arc length to cover both intersections is exactly 1/3 of your circle, of your circumference. And that's because this is like 60 degrees plus 60 degrees if you drew like nice triangles here. Okay, those would be equilateral triangles. So 1/3 of the entire circumference is where it starts. The radii are 1, so the circumference is 2 pi, and 1/3 of that is, well, it's 2 pi over 3. Let's do this. So arc length of 2 pi, that's the biggest one. Here is 2 pi over 3. And what's going on is that right there, if you pick arc length of 2 pi over 3, you can just barely cover it. But unfortunately, just barely cover it, cover both of those intersections, means that your probability just is taking off from 0. Barely. Okay. So this probability is going to start at 0. By the way, if I choose an arc length of 2 pi, for sure I'm going to cover both of those. So that probability becomes 1. And so what that means is that there's this point up here and this point down here. It's actually linear too, I think. Let's find out. I'm going to draw a line first, and then I'm going to try to explain why it should be a line. Okay? Why should it be a straight line? It's because if I knew how much longer I was than my 2 pi over 3, that how much longer I am is sort of like how much slack I have in terms of where I'll start my arc. You know, like if my arc length was a little bit longer than this, I have some slack of like starting it from here or there or there. You can barely see my finger moving, but that's the amount of slack I have. And if I think about the fact that I choose the arc with that length anywhere on the circle, well, then I can just go and, you know, it's like which one of those starting points was it out of the whole circle of starting points. So it's actually going to be that whatever is this green line is however much excess you have beyond 2 pi over 3 divided by this 2 pi that you have. Is that what I want? No, that's not what I want. Hang on a second. Now I want to be more careful. I want to think about this, okay? Maybe I'm wrong. Maybe it's not a straight line. Let's see. So let's suppose that my arc length, this is how you check for sure. Suppose it was 2 pi over 3 plus x, meaning I have a little bit of extra. X is the amount of slack I have. If it's this and I'm putting it around here, and I'm always going to think of my, I don't know why I'm doing clockwise. Mathematicians always do counterclockwise, but it's clockwise now. So if it's clockwise, I'm like, where could I start this 2 pi over 3 plus x in order to be able to cover both of these endpoints? Well, one place I could start it is if I started it right there. And another place I could start it is if I was all the way back x. If I went back by x. And I'm always thinking of making my arcs like this. So my arcs, if I started here and it just went forward, it might look like this. Okay? So I'm always thinking of the arcs as going this way. And these are the starting areas. Okay? So what this is saying is that I'm able to do my start anywhere from like any one of these is okay. So yeah, okay, I see. So I need to start like before this thing. Is that how I want to think of it? I mean, definitely when x is small, then the answer is going to be I can start from any of these divided by 2 pi. Yeah, because I can start anywhere there. It should be divided by 2 pi. So that means that I should be taking a slope which is 1 over 2 pi at the beginning. So the height that I am here, this will be x divided by 2 pi because I could start anywhere there. If I already am over here, I'm out of luck. Oh wow, this is a tricky problem. I'm seeing it's a little bit tricky because as this excess becomes bigger, weird things can happen. Because I could also start here when my thing is long enough and just go all the way around to there. You can see I'm thinking now. What I'm now thinking is I don't like drawing this way. I would rather draw the other way, which is what's the probability that it does not contain both intersections, because something weird is going to happen. I do still know that that point is up there. And I also know that this point is down here. But as my x is small, I'll be taking off at a slope of the height is going to be x over 2 pi. So the slope is 1 over 2 pi. And the reason I'm not super happy with this diagram is because if I go with a slope of 1 over 2 pi, and I go over this distance, which is 4/3, which is 4 pi over 3, then I'll go up like 4/3, which seems too much. 1 over 2. Yeah, it seems too much. Because the slope of 1 over 2 pi, by the way, is this. No, I did that wrong. A slope of 1 over 2 pi is exactly this slope. Okay? And the slope I'm taking off at is parallel to that, so I won't get all the way there. So what I'm seeing is that for a while, it would do something like this. Weird. So in that case, to be more careful, I want to think about the probability that I don't contain. Is that what I want to do? Yeah. So what I want to do here is I want to go and calculate the don't contain. The reason why I'm doing that is because if I want to not contain contains both intersections. No, that's not the opposite. The opposite is like contains less than or equal to 2 of the intersections. You see, the reason I'm pausing here is because when my arc length is like just about that thing, which is just barely beyond a third of my circle, the only way I can manage to cover both is if I start in there and I really manage to cover both this way. But once my arc length is super long, I have multiple ways to cover both. I could like start here and go whoop like this, or I can even start here and go whoop and go all the way around to the other side. Ah, that is still okay. So my brain was still thinking of the complement. The complement is like the other part of the arc, which is the part that I don't pick. In order to not cover both intersections, the missing part, in order to cover both intersections, that's okay. In order to cover both intersections, the missing part must entirely lie inside this side or entirely lie inside that side. That's how I'm going to do it. Okay. Nice, tricky problem. Let's try this more carefully, okay? So I'm going to draw this here. Here's my first circle. Here's my second circle. Now, I need to be careful because I've got like two different cases. And I'm going to think about it as like how much missing arc length is there, okay? So I have the arc length. So I have the arc length. And I also have the missing arc length. Okay? And when the arc length is like less than 1/3 of the total, which is less than 2 pi over 3, I'm not even going to worry about the missing arc length. The last column is just going to be the probability the arc hits both. Hits both. Okay? That's just 0, right? If my arc is too short, less than 1/3 of the entire circumference, I'm dead. Now, I have something in between, which is what if my arc length is between 2/3, is that how I want to think of it? Actually, no, let me still write it this way. So the amount of missing, let's still write the missing. The amount of missing is pretty big. It's bigger than 4/3 pi, 4 pi over 3. And the reason that's important is because now there's no way to cram this 4 pi over 3 entirely inside either this side or that side. That's actually how I want to think of this. I've got these two zones here. One zone is over here, and the other zone is over here. That wasn't supposed to overlap. The other zone's over here. Okay? And what's going on is that this missing part needs to entirely cram in here or entirely cram into there. There's an or there. So now the next part of interestingness for the missing is if the missing part goes of length between like 2/3 pi and 4/3 pi. 4/3 pi is this side here. Okay? So if the missing part is from 2 pi over 3 to 4 pi over 3, then what happens? By the way, what should I do with these endpoints? The answer is it doesn't actually matter because when you do probabilities, the endpoints are like, they're insignificant because it's just one point value and there's infinitely many different possible values for this arc length. So that is actually an insignificant piece. What's much more important is what's going on in between. So this now corresponds to an arc length which is from 2 pi over 3 to 4 pi over 3. Let's actually give it a name, plus x, okay? And that x now is running from this 2 pi over 3 to 4 pi over 3. No, the x is running from 0 to 2 pi over 3. Now, if I'm this big, I'm too big to entirely fit inside this side, so the only way I could fit is if I live over here. And now, from that, the number of different places that I could start, how should I think of this? I see. If that's this thing plus x, well, that's actually 4/3 pi minus x. And that's telling me I have x different starting points. It's the same thing as we saw before. X different starting points for the missing piece divided by the whole 2 pi. So I'm going to write x over 2 pi. And I also want to understand why. The reason is because if I have 2/3 pi plus x as the arc length, the missing part is 4/3 pi minus an x. This is the whole 4/3 pi. So now if I think of it as the Where is the missing starting? Well, suppose the missing starts here and starts to go around this way. Well, I have this x slack before I run into this 4/3 pi minus x, and I really just have to, I mean, at that point I go all the way over and I cram into the end. So I've got x amount of space that I can do this. Well, then I have the last part. The last part is going to be this 4 pi over 3. Well, it's just, no. Missing is now less than 2 pi over 3. And here's where it gets interesting. If it's less than 2 pi over 3, now my arc length can actually fit, my missing part can be here or there. And if I want to parametrize, if I want to think of this as 2/3 pi, no, let's go from the other side. Let's just say 2 pi minus x. Arc length is 2 pi minus x. If I have 2 pi minus x, the missing is just x. This is just x. So I'm going to have to ask, how do I put some arc of length x somewhere? Is that nice? I'm seeing lots of negative signs. Well, it's what we got to do. Okay? So if it's 2 pi minus x, the missing length is x. I have two ways to do that. I can either put the missing thing of x long this is supposed to be a thick line, okay? I can either put the thing of x over there, or I can put the thing of x over here. Now, if my thing is x long, and there's 2 pi over 3 total space, then there's like 2 pi over 3 minus x different starting places that I can use before, so if this whole thing is not different starting places, but I have a length of 2 pi over 3 minus x for which I can start and still do an x and still fit inside this 2 pi over 3. So in order for me to have my missing thing entirely lie inside there, that is a 2 pi over 3 minus x. But that's not the only thing I do. Okay, that's 2 pi over 3 minus x on that side, but I also have something on this side. So on this side now, if my thing is x long, well, I have 4 pi over 3 space. So the same calculation tells me plus 4 pi over 3 minus x. It's raining here. Yeah, it's the drum roll. It's telling us that we're getting close to the answer. So if I add these together, now what I get is 2 pi minus 2x. Aha! This is good. This is good. So what I just saw is that when I'm going down from 2 pi on the arc length, if I go back down by x, in fact, my probability goes down by 2x. So there's a slope of 2. That's how I catch up. So what's going on is that at some point here, this is at 4 pi over 3. Okay, let's clean this off. This is at, well, let's draw it better. This is at 4 pi over 3. And I go up with a slope of 1 over 2 pi until there, and then it takes a sharp increase. That's actually what's going on. So on this part, I have a slope of 1 over 2 pi. And this part, I have a slope of 2 over 2 pi. Okay. And does that make sense? Let's look at this. It's because over here I can also see that, wait, what in the world did I do? No, it's not. It's not 2 pi minus 2x. I have to divide by 2 pi also. These aren't probabilities. This is like lengths of which I can start. That whole thing needs to divide by 2 pi. Over 2 pi. Fortunately, it does not change my calculation. This has to divide by 2 pi. But fortunately, when I say it doesn't change my calculation, back over here, what we've got is that the slope is going to be 2 over 2 pi, and that's also what you see here. This is 2x over 2 pi. Excellent, that's right. Okay, so now what we did with all of this is, well, if I want to know what's the total probability, well, here's what I would do. I'm going to be picking any one of these arc lengths from 0 up to 2 pi, and then I'll decide for each of them I have some probability that it works. So the answer to the whole question actually is going to be that I take this whole region And I need to know what fraction of the region is under this part. I need to know what fraction of this whole rectangle is under this part. The reason is because it goes all the way up to 1. So, I mean, what this is saying is that for each particular arc length choice, this is like how much of that probability I should be able to eat. Okay? So in that case, let's see. What is this? Well, I guess we got like some triangles to add up. A triangle and a trapezoid. Okay, let's see. Let's finish this up. So we need to go and find the triangle over here. And how high is it going to go? Well, it goes over by 1 over 2 pi. So, no, sorry. It goes over by 2 pi over 3. And it goes up by 1 over 2 pi. So the height of this is 1/3. This is at 1/3. And that makes sense because I'm supposed to go up and then go up by twice as much. So if that's 1/3, let's look at this. Let's draw this vertically. Now I just need to know, like, as a fraction of that entire rectangle, what is this? What's the easiest way to do this? I see. So the easiest way to do this is to go and say, yeah. So this thing here, this is part of 1/3 of the rectangle. Okay? I'm going to turn everything into fractions now. So I want to know what fraction of the whole rectangle is this tiny triangle here. Well, this tiny triangle, I have 1/3 of the base of the rectangle, but I don't have the whole height. In fact, I don't even have 1/3 of the whole height. If I did 1/3 of the whole height, that would be here. Okay? So, for example, if I made this tiny rectangle right here, that would be 1/9 of the entire area of the whole big rectangle. But I only have half of that, so it's 1/18. So this particular piece is 1 over 18. Okay? So if that's 1 over 18, well, let's look over here. Well, I can say that this thing here, this is actually half of 2/3 of the height. So if I just move this part of the triangle down over there, actually what I can think of over here is I'm going up 2/3 of the way with a full rectangle. So in that case, what is the area of this piece? Well, I get 1/3 of the entire thing's width and 2/3 of the entire thing's height. That's 2/9. So between these two, I'm getting 2/9. And finally, we add everything up. So finally, if I want to know what's the area, what's the fraction of the area that's under all of this stuff, it's 1/18 plus 2/9. Let's see if this works. 1/18 plus 2/9 is equal to something over 18. 1 plus 4. So that's 5 over 18. Okay, let's see if this works. 23. Huh? That's not a probability. All probabilities have to be between 0 and 1. Something's telling me that it might be that whoever was writing the slides for me forgot to ask to add together the top and the bottom. Because I'm seeing 23 and I'm like, well, I'm pretty sure that that's going to be 5 plus 18 because 5 plus 18 is 23. So I'm going to guess that the question says add top and the bottom and there was just a typo as somebody was giving me the slides. But I'm also seeing that Debbie, the moderator, says that add top and bottom is what you should do. That means you should say 5 plus 18 and it's 23 and that is the answer. Okay, how are we doing on time? We have only 5 more minutes of time. Given how long it's taking me to do these problems, let's see, what should we do? I'm looking at, I'm actually going to do this, okay? So I don't think we can solve another question in just 5 minutes, especially because they're getting more challenging. AMA, it's time to ask math anything in the sense that, let me do some more general questions because I see that somebody already started putting, somebody has started putting like other kinds of questions into the chat. So somebody said, math hobbyist here. How do you guys manage to deal with frustration when learning new topics? I taught myself more abstract algebra and graph theory, but things started getting very challenging. So my answer to that question is, when learning new topics, it's a lot easier when there's somebody helping to guide you who shows that, the question is interesting somehow. Because when I was first learning abstract algebra, I didn't even know what it was for. And that made it very difficult to stay concentrating, because if I just don't know why it's even useful at all, then it's very hard to just say, let's dig in and understand everything. For me, I was lucky that when I went to college, there were actually some very good professors who were able to explain why it was interesting. But other people find it interesting if they get to learn with other people. So if you can find other people to also think about things with and share insights about that abstract stuff you're learning, that can be more fun too. Other questions. I see all these things have come in. Somebody asked, will you do something special next week? I don't know. I don't think we have another special one, so it's just going to go back to Ask Math Anything. There's somebody asked, what level of math was the question we just did? Actually, this is calculus in disguise. This is an integral. But nevertheless, I tried to explain it in a way that's sort of like geometry. So this is sort of like a little bit of calculus in disguise. This is about probability and about geometry. And it was tricky. If you can see, it wasn't just a straight line. We had to be careful, and you saw that I caught myself along the way. More stuff here. How do you do counting and probability problems? They're impossible for me. Don't worry. What you see here is that we just did a probability problem by making sure we understood like what's the top, what's the bottom, and being careful not to have an oversight of like the cases in which it is okay. The reason why counting and probability problems are hard is because it can be very easy to forget that there might be some change in the behavior of the problem depending on, for example, the arc length. Because as you saw, suddenly when the arc length got too long, something weird happens. So I guess it's important to be able to notice when there are these funny things happening when you're doing these problems. How do you do questions involving infinite operations, like 1 plus 2 plus 3 and so on? That's infinity, or negative 1/12, depending on how you like it. Well, those kinds of questions, it's best to think about what happens if you have a finite sum. If you add up only a finite number of them and then see, like, what is that? Can you try to get a formula for that and show that that formula gets closer and closer to something else? Usually when I see those kinds of things, I usually hope to find what's called a telescoping sum. I like to be able to show that each term is something minus something, and I want lots of canceling to happen. How to grow a big brain? You should eat food. Please tell me you got other hobbies aside from math. What are they? I love going to different parts of the country, different parts of the world every weekend to go and give math talks. I just came back from Las Vegas this morning. Food equals survival equals chances to get smart. Yes, that is the words of wisdom for today. How much food? As much as reasonably comfortable, not too much, obviously. What's your favorite food? All kinds of different things. I've answered this already on the live stream, but I like spicy food. Oh, hello from a fellow CMU person. Hello, hello. Eat fish, it make you smart. Actually, it's true. I used to have some friends who worked at Google when Google was really early on. And when Google was really early on, they had some chefs who came to make food for people so they wouldn't have to go out to eat outside. And I believe that they actually used to always make sure that there was a fish dish as well. Lots of bananas. You guys watched my live streams. Somebody asked, I saw somebody else ask, soy milk, almond milk, or milk, cow milk. I guess I usually drink cow milk. I also like soy milk, although I prefer like the soy milk from Chinese supermarkets, which is different from soy milk from standard supermarkets. I'm not really a big fan of almond milk. Okay. Oh my. Somebody asked, do I like junk food? No, it makes me feel bad. I just don't like junk food. Oh my. Okay. Let's finish with this one. What are you always happy? Even when resolving hard problems, do you get mad? Tell me your secret. Well, I don't know. I'm happy because it's interesting to think about these, okay? So if you give me something that I don't know how to do, it's a sport. And I want to be able to do it. So I think it's interesting. If I can't do it, then it makes it more interesting. Will I get mad? Not really. What's there to be mad at? It's more of just, gee, I wonder if I can think of something else. This is actually kind of interesting. So yeah, and of course on this live stream, it's very hard to be mad when out of the corner of my eye, I see all of these very funny chats that are going on with all of you. With that, unfortunately, we'll have to close for the day. So that was the Fall Math Meet, a little preview of a little coverage of some of their problems. Congratulations to NanoMath for putting this on. And I'll see you next week with a normal Ask Math Anything right back on this channel. Bye-bye.